Hi everybody, today we're looking at vectors and it's an introduction to vectors. So you may be aware of some of these things already, but we will develop and extend our understanding in future lessons. But just to start with, a definition of collinear and coplanar. So 2 points are collinear if they lie on the same line, and 2 points are coplanar if they lie in the same plane. There will be terms that will come up continually throughout our topic, and so I thought I'd start with definitions of those. But if we then look at a vector, it's a quantity that's fully described both by magnitude and direction, or size. So where with numbers, we just talk about the size of the number, like the size could be 5 or 7 or 10. With a vector, we don't only have that size, but we also have a direction that it's headed. And we represent it by a directed line segment. For example, that could be a vector. The length of the vector indicates size, and we've got a direction by the arrow. Or we could have a different one that goes down like that, for example. Now, we're talking about directed line segments and vectors. The textbook does it in a different way, and it's much more roundabout. They talk about a line segment is part of a straight line bounded by 2 points. So if I've got a point there and a point there, then that's one line segment there. And then a directed line segment is a line segment that has direction. In other words, and we've already seen what that looks like, but if those are my 2 points, then the directed line segment has a direction with an arrow. And if this is A and this is B, then we can say it's AB, and an arrow above the AB indicates that it's going in the direction from A to B. Now, they then say that two directed line segments, AB and CD, are called equivalent. And they've got a symbol there for equivalent. But what they're saying is that that's only true if and only if the line segments AD and BC have a common midpoint. Now, AD is from the start of AB to the end of CD. So it's this line along here. And then CD, so from the start of CD to the end of AB is my line segment BC or CB. It doesn't matter whether, because we're just talking about a line segment in these cases, not a directed line segment. If they have a common midpoint, then that means that AB is equivalent to CD. Now, as a result of that, we're just relying on the idea of the diagonals of a parallelogram meeting at a common point, having a common midpoint. So that's what's going on there. And then they say a vector is a collection of all equivalent directed line segments. So I get a best guess way to think about this is that a vector doesn't have a particular position in space, whereas a directed line segment does. So, for example, if I define 2 points, let's say that's A and that's B, my line segment AB is going from point A to point B. But the vector that this directed line segment represents could be anywhere. It could be there. I've got to have it the same length because could be there, could be there, could be there. So while we're only going to, so the directed line segment AB is just this one here. All of these that are going in the same direction with the same length are all the same vector. Okay, don't worry too much about that. That's not a key thing, but I did want to just explain why the textbook went in a different way. So, what's a position vector? Well, it's a vector from the origin to any point, or to a point. That's the position vector of the point. So it's describing it relative to the origin. It's basically saying, how do we get from the origin to some point? So if I put a point in space A and I start at O, which is the center of my three-dimensional origin, then the vector from O to A is the position vector of A. Now I should just mention that this is X, Y, and Z. So OA is a position vector of A, or I could put another point down here, B, and it's OB. So we're going from the origin to B. So position vector's got to tell us from the origin, how do we get to the point? So that's the position vector of B. A displacement vector is if we've got 2 points, so let's say A and B, and the displacement of B from A is just the vector between the 2 points. So the displacement of B from A is AB. Okay, and that's a displacement vector. Now, if we're looking at addition and subtraction of vectors, well, let's think about how we added numbers first. So if I was to do 2 plus 3, I'd start at 2, so I would have gone from 0 out to 2, and then I'd be adding 3 on. So 1, 2, 3, and that gives me 5. But let's say we represented it with one-dimensional vectors, so vectors that just go along the straight line. I could represent 2 by the vector going from 0 to 2. So that would be 2. And then then the vector 3 would be the vector from 0 to 3. But then if I added that, what I could do is I could take this 3 vector and put it on the end of my 2 vector, and so that would get me to an answer of 5. So using this same idea, to add 2 vectors, we can just say that you put at the end of the first vector, you place the start of the second vector. So that should be the word vector. So let's see how this works. We've been asked to add these 3 vectors. Okay, so AB is 4 spaces apart. So I'll start here, go 1, 2, 3, 4. So that's AB. And then what I've been asked to do is I've been asked to add CD. So that goes across 1 and up 3. So I'm going to put CD at the end of AB. So I start from this point, I go 1 across and 3 up. And so then that's CD. And I've actually run out of space, so I'll just adjust that. And then finally EF. So I put that, so I start from the end of CD and then I go across to and up to. And so then that is adding the 3 vectors. Now, the addition of 3 vectors has to be a vector itself, and so the vector is from the start where we started to the end point where we finished up. And so that's AB plus CD plus EF. And so probably my notation there is a little wrong. I should just draw it as a directed line segment like that. So the addition of 3 vectors is a vector itself, and it's from the start point of the diagram to the end point of the diagram. So, and then subtracting a vector, we just think of it as adding a negative vector. Now, a negative vector is going to have the same size, but it's going to go in the opposite way. Now, we're using A, B, C, D, and E, F as above, but so A, B is still positive. So that's 1, 2, 3, 4. Now, C, D has to be going in the opposite direction. So we'll be starting at D and going down to C. So that's down 3 and across 1. And we've got to start that. So this time we're going to have point D at the end of AB. So then it's down 3 and across 1. So it's down there. That's the vector going in the opposite direction. And then for EF, we're starting here, we're going across 2 and down 2. So across 2 and down 2. And so then the negative vector is that one there. And so then this subtraction, well, it's from the start of my diagram to the end of my diagram. And so it looks like that. So that's my subtraction AB. Take CD. Take EF. Now the zero vector, well, it has no magnitude, no size or a size of 0, and therefore no direction. So show that in a triangle ABC, AB plus BC plus CA equals 0. Well, if I look at that, if I do AB plus BC, then the addition of those two is from A to C. So AB plus BC is equal to AC, which is the negative of CA. And so then you could say AB plus BC plus CA is equal to negative CA plus CA, and so then that's 0. Scalar multiple of vectors is where we're multiplying a vector by a number. Now if the number is positive, the magnitude is going to get bigger, but the direction stays the same. Well, the magnitude is going to get bigger if it's more than 1. It's going to get smaller if it's less than 1. And then a similar thing happens if it's negative. So if the modulus of my number is more than 1, it's going to get larger. If the modulus of the number is less than 1, then it's going to get smaller, but the direction is going to reverse. So if one vector is a scalar multiple of another, then the vectors must either be parallel or collinear. So if I have a vector that looks like that, and I've got another vector which is double its size, well, potentially we may be able to draw it over the top. So same direction, but double the size, or it could be in a different position, like that. And so we can see that the green is parallel with both the black and the blue. But if it's the black and the blue, well, the points on those, or the vectors, are lying along the same line. Alright, so we've got to draw 3 lots of A and and add that to 2 lots of B. So 3 lots of A, well, it's positive, so the direction is going to stay the same, but it's going to be 3 times as large. So if I start it down here, I'm going to go across to and up to, that's A itself, but it's got to be 3 times as large. And so then 3A is just 3 lots of A put together. And then we're adding 2 lots of B. So 1 lot of B is just from there to there, and a second lot of B is all the way across. So that's 2B. And so then the addition of those is from the start to the end, So that's 3a plus 2b. Okay, so that's part A, and then for part B, it's half of A. So instead of going across 2 and up 2, I'm just going to do half of that, so it's across 1 and up 1, so that's half of A. Take 2/3 of B, so we're going in the negative direction with B. B is 3 spaces, so 2/3 is going to be 2 spaces. So I'm going across in the opposite direction. So it was a half of A, and this is 2/3 of B. And so then the direction, or the final, is the direction from the start to the end. And that's quite a small diagram. Okay, alright. And then the last one, we're given a parallelepiped. Now, you probably haven't come across that, but it's a 3-dimensional. It's a 3D version of a parallelogram. And it's a prism. So if you think about it, something like a rectangular prism or a cube are 3D versions of rectangles or squares, which are prisms. This is the same idea, it's just a 3D prism version of a parallelogram. Okay, so we've got it there. We've been defined as having A, B, and C. You can see that they're marked by directed line segments. And we've got to find the addition of A, B, and C, or the linear combination, so that's the addition or subtraction, and each of them can be multiplied by a certain number to find FD. So FD is from here down to there, which means you've got to start at F and get to D, so we're ending up. So I go this way, and I go this way, and I go down here. There are probably some other routes, but that still give you the same number. So FD is equal to FE plus EH plus HD. Now, FE is the vector A, but just in the opposite direction. Because this is a parallelogram, opposite sides are equal and parallel. So it'll be the same vector, whether it's FE or BA. So it's negative A, so it's going in the, it's equal to A, but going in the opposite direction. Now, EH is going in the same direction as B and is equal in length. And then HD is going down, whereas C is going up, so they're the same length, but it's going in the opposite direction. So it's negative A plus B, take C. Now MA, where M is the midpoint of CG, so M is here and we're going back to A. So I'd come down here, I'd go along here, and along here. So MA, well, it's half of GC plus CB plus BA. So a half of GC, well, GC is going down, but it's the same length as C. So it's a half of C, negative a half of C, because C is going up, but GC is going down. So it's negative. CB, well, CB is going in the opposite direction to B, but it's the same length. And BA is the opposite direction to A, but the same length as A. And so it's negative a half C, take B, take A. Okay.